Myself, Dr. Sachin Kumar, welcome you in lecture series of Module 3 Differential Calculus 2nd. Topic of my today lecture is Euler's theorem for homogeneous function. In this lecture, I will take a topic of homogeneous function, degree of homogeneous function, Euler's theorem for homogeneous function, and at last I will discuss problems of application of Euler's theorem. So let us start with homogeneous function. A function u equals to fxy is said to be a homogeneous function in variables xy of degree n if it is expressible in any one of the following form. U equals to x raised to the power n into 5y over x, or u equals to y raised to the power n into omega x over y. In this notation, u equals to x raised to the power n 5y over x. Phi is a function having terms in form of y by x, while in this form omega is a function having terms in form of x over y. Some important points about homogeneous function. Any polynomial function in two variables x and y is said to be homogeneous if all its terms are of the same degree. For example, the function fxy equals to x cube plus 3xy square minus 5x square y plus y cube is a homogeneous function in xy of degree 3. As we observe that degree of each term, first term, second term, third term and last term, each exactly 3. So it is a homogeneous function in variables xy of degree 3. Second point, in case of non-polynomials, a function u equals to fxy in two variables xy is said to be a homogeneous function of degree n if for any positive number mu, f of mu x mu y equals mu raised to the power n into fxy. This means if we replace x by mu x, y by mu y in this relationship, then function u must take a form mu raised to the power n into fxy. That is, mu power n should be outside the function. For example, function fxy equals to cos x square plus y square over 2xy will be an homogeneous function in two variables xy of degree 0, as we can verify by replacing x by mu x and y by mu y in this function. We get cos, here x in place of x, if we write down mu x, we shall get mu square x square. In this term we shall get mu square y square, and in denominator we shall get 2 into mu square xy. From here we observe that mu square will cancel out, and if we cancel out mu square, then outside we can write down mu raised to the power 0. That is, there will be, if we cancel out mu square from numerator and denominator, inside the function there will be no power of mu, only mu raised to the power 0 will be outside the cosine function. Therefore it is a homogeneous function in two variable xy of degree 0. Another example, function fxy equals to x square tan inverse y over x will be homogeneous function of degree 2 in variables xy, as it is identical with the form fxy equals to x raised to the power n phi y over x. Here function phi is represented by function tan inverse and term is of y by x form. The power of x here is 2 and in standard form it is n, so by comparison we get n equal to 2, so it is a homogeneous function in xy of degree 2. But the function cos inverse x square over y is not homogeneous function of xy, since if we replace x by mu x, in numerator I will get mu square x square, in denominator I will get mu y. So 1 power of mu from numerator will cancel out with mu in denominator, but still 1 power of mu, that is mu x square, will left inside the function, that is mu cannot be taken out this cos inverse function, so it cannot be a homogeneous function in variables x, y. Third point, if u equals to f x y z is a homogeneous function in 3 variables x y z of degree n, that it can be expressed any of these 3 forms. Either mu equals to x raised to the power n function of y by x, z by x, or u equals to y raised to the power n phi x over y, z over y, or mu equals to z raised to the power n phi x over z, y over z. That is, if we take power of x common, we shall get this form, and if we take y raised to the power n common, we get this form, and if we take z raised to the power n common, we get this form. From all these 3 forms, we get same degree of u, which is n. Euler's theorem for homogeneous function statement: if u equals to fxy be any homogeneous function in 2 variables xy of degree n, then x del u by del x plus y del u by del y equals to n times of u. Proof: since u equals to fxy is homogeneous function in 2 variable xy of degree n, therefore it can be expressed as uxy equals to x raised to the power n into phi y over x. Now differentiating equation 1 on both sides partially with respect to x, we shall apply product rule. Since x raised to the power n is the function of x, phi is also a function of x. So del u by del x will becomes, if we differentiate x raised to the power n, we get nx ki power n minus 1, while phi y over x is kept as such. In the second term, x raised to the power n is kept as such. If we differentiate phi with respect to x, we get phi dash y over x, and then derivative of y over x with respect to x will be minus y upon x square. Similarly, if we differentiate equation 1 partially with respect to y, x raised to the power n will be treated as constant. We need to differentiate only phi with respect to y. So del u over del y will equals to x raised to the power n phi dash y over x. If we differentiate y over x partially with respect to y, treating x as constant, we shall get 1 over x in product. Now multiplying equation 2 by x and 3 by y, and then adding, we get x del u by del x plus y del u by del y. Now see the RHS. If I multiply this by x, here I will get nx raised to the power n phi y over x. Here x square is in divide. If I multiplied with x, here I will get only x. So after simplification I will get x raised to the power n minus 1 phi dash y by x multiplied by minus y. So del u over del x will have n x raised to the power n phi y over x minus y x raised to the power n minus 1 phi dash y over x, which will correspond to this term after multiplication of x and simplification. Similarly, in RHS, terms corresponding to del u over del y after multiplying with y will be y into x raised to the power n minus 1 phi dash y over x as this term. From here we observe that last term are equal, but with opposite sign will cancel out. On simplification we get x del u by del x plus y del u by del y equal to nx ki power n phi y over x. So x raised to the power n phi y over x is nothing but the value of u, so we replace it by u and get x del u by del x plus y del u by del y equals to nu, which complete the proof of Euler's theorem. Some important note: if u equals to f x y z is a homogeneous function in 3 variables x y z of degree n, then by Euler's theorem we shall have x del u by del x plus y del u by del y plus z del u by del z barabar nu. The basic change here is that u is the function in three variables x, y, z. That is, the statement of Euler's theorem for two variables may also extended for function of three variables, which must be a homogeneous function in x, y, z. Okay, so for function of three variables we get x del u by del x plus y del u by del y plus z del u by del z equals to nu. Example, if u equals to root x plus root y whole power 5, then find value of x del u by del x plus y del u by del y. Here we shall apply Euler's theorem, since from here we observe that u equals to root x plus root y whole power 5 will be a homogeneous function, as the degree of each term will be same. So we firstly find out the degree of this function. For this we take root x common from here. If we take root x common, whole power 5 already x exists, root x means x raised to the power half. So root x whole power 5 will be outside, and inside we shall have 1 plus under root y over x. Y over x is totally within square root sign, whole power 5. So root x power 5 can be written as x raised to the power 5 by 2, 1 plus under root y by x whole power 5. This term is nothing but some function in y over x. So this function is identical with u equals to x raised to the power n 5 y over x. So by comparison we get that u is a homogeneous function in xy with degree n equals to 5 by 2. Here x raised to the power n, here x raised to the power 5 by 2. So on comparison we shall get n equals to 5 by 2. Therefore by Euler's theorem for homogeneous function of degree n, we shall have x del u by del x plus y del u by del y barabar n times of u. Here n is 5 by 2. Putting the value of n, we get x del u by del x plus y del u by del y equals to 5 by 2 u. Next example, verify Euler's theorem for homogeneous function u equals to x raised to the power 1 by 3 y raised to the power minus 4 by 3 into tan inverse y by x. Here we have u equals to x raised to the power 1 by 3 y raised to the power minus 4 by 3 tan inverse y over x. So to check its nature, we replace x by mu x, y by mu y in equation 1 in such a way that here we get, from here we shall get mu raised to the power 1 by 3. From here I will get mu raised to the power minus 4 by 3. The total power of mu will be 1 by 3 minus 4 by 3, and x raised to the power 1 by 3 y raised to the power minus 4 by 3 will be as such. In inverse function, if I replace mu by mu y and x by mu x, mu will be cancelled out. We shall get y over x only. So if we simplify it, we get u equals to mu raised to the power minus 1 x raised to the power 1 by 3 y raised to the power minus 4 by 3 tan inverse y over x. Clearly u is a homogeneous function in variables xy of degree minus 1. Therefore from Euler's theorem on homogeneous function, we must have x del u by del x plus y del u by del y equals to minus u. Minus u means n times of u. If we replace n barabar minus 1, we get minus u. Now in this question we need to verify the theorem. So we obtain the result by Euler's theorem. Now we shall get same result by partial differentiation method. For this we differentiate equation 1 partially with respect to x. If we differentiate it partially with respect to x, y raised to the power minus 4 by 3 will be constant, so it will not be differentiated as it is in product form. So we need to differentiate x raised to the power 1 by 3, which is in product with tan inverse y over x. So applying product rule, first we differentiate x raised to the power 1 by 3, derivative of x raised to the power 1 by 3 will be 1 by 3, x raised to the power 1 by 3 minus 1, y power will be as such, tan inverse we kept as such. Out of 2 we differentiate x raised to the power 1 by 3 and kept tan inverse y by x as such. In the second term, x raised to the power 1 by 3 will be kept as such, y is a constant term, will be kept as such. Now the derivative of tan inverse y over x will be 1 upon 1 plus y over x whole square, and if we differentiate y over x partially with respect to x, we shall get minus y over x square in the product. Similarly, if we differentiate equation 1 partially with respect to y, in this case x raised to the power 1 by 3 will be outside the differential operator. We need to differentiate these two terms by product rule. So in this, x raised to the power 1 by 3 as such, if we differentiate y raised to the power minus 4 by 3, we get minus 4 by 3 in the product, and y power becomes minus 4 by 3 minus 1. Tan inverse y over x is kept as such. In the second term, this is a constant term, we kept first term as such and differentiate tan inverse. Derivative of tan inverse will be 1 upon 1 plus y over x whole square multiplied by 1 over x, as derivative of y by x with respect to y will be 1 over x. X will be treated as constant. Now multiplying equation 3, this equation by x, and equation 4, this equation by y, and then adding. If we multiply this equation by x, so after multiplication with x, in first term x power will be 1 by 3. In the last term, if we multiply it by x, here after simplification I will get minus y over x. Similarly, if I multiply this by y, then here power of y after simplification will become minus 4 by 3, and in second term here I will get y in product, so this term will be y over x as shown here. X del u by del x plus y del u by del y equals to 1 by 3 x raised to the power 1 by 3 after multiplication with x, y raised to the power minus 4 by 3 tan inverse y by x. In the last term, this is the change. So x raised to the power 1 by 3, y raised to the power minus 4 by 3, 1 upon 1 plus y over x whole square, product we have minus y over x. And from del u over del y, we get minus 4 by 3, x raised to the power 1 by 3, y raised to the power minus 4 by 3 after multiplication with y. Power will become y raised to the power minus 4 by 3 tan inverse as such, and in the last term, here 1 by x will be multiplied by y, so it will become y over x. From here we observe that this and this term are same with opposite sign, so we'll cancel out and we simplify these two terms and get x del u by del x plus y del u by del y equals to minus 1 into x raised to the power 1 by 3 y raised to the power minus 4 by 3 into tan inverse 1 by y by x. So this is nothing but value of u. The value of u multiplied with minus 1 will give you minus u. So from equation 2 and 5 we conclude that Euler's theorem is verified, as both result obtained are same. Next example, if u be a homogeneous function in two variables x, y of degree n, then so that x del to u over del x square plus y del to u over del x del y equals to n minus 1 into del u by del x, x del to u over del x del y plus y del to u over del y square equals to n minus 1 del u over del y. And at last, x square del to u over del x square plus 2xy del to u over del x del y plus y square del to u over del y square equals to n into n minus 1 u. So we start with solution. Here u is given to be a homogeneous function in variables xy of degree n. So by Euler's theorem for homogeneous function, we shall have x del u by del x plus y del u by del y equals to nu. Now if we see first result, we need del to u over del x square, which will be obtained from first term when we differentiate equation 1 partially with respect to x. So firstly we differentiate equation 1 partially with respect to x. Now if we see, first term will have two function of x in product, so product rule will be applied, x such. If we differentiate it again with respect to x, we shall get del to u over del x square, plus in second term we shall differentiate x, its derivative will be 1 and del u by del x will be kept as such. And this term if we differentiate with respect to x, y will be treated as constant, and differentiating this term I will get del to u over del x del y. On RHS n is a constant, derivative of u with respect to x will be del u by del x. So we got x del to u over del x square plus del u by del x plus y del to u over del x del y equal to n del u by del x. Now if we take this term in RHS and simplify, we get x del to u over del x square plus y del to u over del x del y equals to n minus 1 into del u by del x. Again differentiating equation 1 partially with respect to y. If I differentiate equation 1 partially with respect to y, x will be treated as constant, its derivative with respect to y will be del to u over del y del x, and in last term we shall apply product rule. Y will be kept as such, it will be differentiated with respect to y and we get del to u over del y square. Again if we differentiate y with respect to y, we shall get 1 and this term will be kept as such. And in RHS we shall get n is a constant, del u over del y as shown in this equation. X del to u over del y del x plus y del to u over del y square plus del u over del y equals to n del u over del y. If I take this term here, I got x del to u over del x del y. I have written here del x del y, while here I have del y del x. As these two derivatives are equal, we have discussed in previous lecture, so we can replace this by this, plus y del to u over del y square will equals to n minus 1 del u over del y. Now to get the third result, we multiply this equation 2 by x and this equation 3 by y and then add. If we did so, here will be x square del to u over del x square, here I will get xy del to u over del x del y. Similarly in this equation in LHS I will get xy del to u over del x del y. If I add these two, these will be twice since both will be same, and in this term I will get after multiplication with y square del to u over del y square. And on RHS from here I will get n minus 1 is common in both, will be taken common, x del u by del x from this and y del u by del y from this. So on multiplying with x and y and then adding, we get x square del to u over del x square plus 2xy del to u over del x del y plus y square del to u over del y square equals to n minus 1 x del u by del x plus n minus 1 into y del u over del y. N minus 1 is taken common, we get this, and from Euler's theorem this value will equals to nu. So if we replace this term by nu, we get x square del to u over del x square plus 2xy del to u over del x del y plus y square del to u over del y square equals to n into n minus 1 u. Next example, if u equals to x square minus 2xy plus y square whole power 3 by 4, then apply Euler's theorem to evaluate value of x square del to u over del x square plus 2xy del to u over del x del y plus y square del to u over del y square. Now to solve this question, we shall use this result. This result is known as statement of Euler's theorem in terms of second order derivative term. So this is also a statement of Euler's theorem for in terms of second order derivative term of u. So it can be applied in problem directly, and we shall apply the same in this particular example. Here u equals to x square minus 2xy plus y square whole power 3 by 4. From here, if I take x square common from outside, so x square will be taken common. Here I have power 3 by 4, x square power 3 by 4. After simplification will get x raised to the power 3 by 2 outside, and inside I will get 1 minus 2y over x plus y over x ka whole square. That is, this function will become identical with u equal to x raised to the power n phi y over x. So in the similar way, if we simplify it for finding degree of this homogeneous function, we shall get n equals to 3 by 2. Therefore, by Euler's theorem for second order derivative, we shall have x square del to u over del x square plus 2xy del to u over del x del y plus y square del to u over del y square equals to n into n minus 1 u. Now we put value of n as 3 by 2, we get x square del to u over del x square plus 2xy del to u over del x del y plus y square del to u over del y square equals to 3 by 2 into 3 by 2 minus 1 into u. After simplification, we get 3 by 4 into u. This is the value of desired second order partial derivative term. Thank you.